DeepSeek has taken the world by storm. We are living in an era where an AI model wipes off 1 trillion from the stock market. Since we are also an AI channel, we have to talk about this. Hi, my name is Joydeep. I have 14 years of experience working with top companies in AI, and in this channel, I talk about GenAI career in the industry. Please like this video and subscribe to the channel, as this will motivate me to continue working towards bringing you the latest trends in AI. Welcome to my channel. So first we'll look at the chat application, chat.deepseek.com. It looks very similar to the ChatGPT application. To enable it to ask using R1 model, which is the latest model that they have shared, this is the select this deep think R1 button. So now you can ask your questions here. Create fun math. You guys also give this a try for your everyday puzzles. So here it's doing the thinking. So you can see the point is that it has used more tokens for doing the thinking, and then it has come up with the answers. As part of this release, the most famous model that they have shared is the R1 model, which you can see here in Hugging Face under the DeepSeek AI organization. And so here is the R1 model. Here you can see they are mentioning R1 Distill Llama models, Distill Quen models, and Distill Llama 70 billion. So we'll understand what this means later. There is the V3 class of reports as well. V3 class of models as well. We have the technical report here. Although if you go here, so it's going to the archive link, which you can read here. We'll go through the main points of the different papers. The easiest way to run R1 locally is using Ollama. So I'll go to the terminal. DeepSeek run Ollama run DeepSeek R1 1.5 billion model. For me, the model is already downloaded, but if you're running this command for the first time, it will download the model. Think of a fun math game similar to Sudoku, but good for 5-year-old kids. Let's see what it comes up with. So it starts with the thinking tokens. I also have a video on running Ollama and running LLMs locally. Please check it out. So the answer is finally done. Generating this took around 5 minutes on my laptop. So we start with the architecture of the model. So in the R1 model, they are using the DeepSeek V3 base as the base model, which uses the mixture of experts model. So this is the mixture of experts diagram from mixture of experts model diagram from the V3 paper. So DeepSeek R1 builds upon the foundational achievements in the DeepSeek V2 and the DeepSeek V3 models, specifically mixture of experts and multi-head attention, and from DeepSeek V3 specifically multi-token prediction, and integrating all of them for better performance. This is the overall mixture of experts model as shown in the figure here. As you know, the transformer block has RMS norm goes to attention module, and then there is another RMS norm, and then there is the feed forward norm. If you see the attention is all you need, or the previous models there was the layer norm, but LLMs these days use RMS norm, as it is seen that they have faster training convergence, also computationally they are faster. So instead of this feed forward network here, they have the DeepSeek mixture of experts model here, which is basically you pass through n shared experts and r routed experts. The shared experts are always active, capturing common knowledge applicable across various contexts. Other experts are called routed experts, and information is routed to them using an optimal load balancer. The load balancer is learned using combination of various balance losses such as expert level balance loss plus device level balance loss and communication balance loss. In DeepSeek V3, they made various improvements to the this mixture of experts architecture and training process. The key improvements include an auxiliary loss-free load balancing, complementary sequence-wise auxiliary loss. There is this node limited routing, and enhanced sparsity constraints. These advancements contribute to more efficient training, faster inference, and superior performance compared to DeepSeek V2. Another important improvement that they have made is in this multi-head attention part. So they introduced something called multi-head latent attention. In the original Transformers paper, multi-head attention is used. A common method to make the inference faster is using key value caching or KV caching. We reuse the previous keys and values instead of recomputing at each step. This figure is from the KV caching blog of Hugging Face. So KV cache is implemented as a rolling buffer. At each decoding step, only the new query Q is computed, while the K and V stored in the cache will be reused, so that the attention will be computed using the new Q and reused KV. Meanwhile, the new tokens K and V are also appended to the cache for later use. So you can understand that the speed up achieved by KV cache comes at a cost of memory. To apply KV cache, you need batch size, cross sequence length, cross hidden size, cross number of heads amount of memory. Thus, for larger batch size and longer sequences, this is a problem. In order to reduce this KV cache, they introduced something called the multi-head latent attention. In here, they compare between multi-query attention and grouped query attention. So for DeepSeek V2, they introduce an innovative attention mechanism called multi-head latent attention, equipped with low key value joint compression. MLA achieves better performance than normal multi-head attention, but requires a significantly smaller amount of KV cache. So let's see how it's there. A single key and a single value head is shared across all query heads. This can significantly reduce memory usage at the cost of accuracy of attention. To improve the accuracy a little bit, grouped query attention is there, where a single pair of key and value heads will be shared only by a group of query heads, not all queries. That's like halfway between between multi-head attention and multi-query attention. In DeepSeek V2, they apply something called low-rank joint compression for keys and values to reduce the KV cache. So low-rank key value joint compression. So the core of MLA is the low rank joint compression for keys and values to reduce KV cache, where CKV belongs to RDC is the compressed latent vector. So there are compressed D dimensions for keys and values. So this denotes the KV compression dimension WDKV cross D. So compressed dimension cross D is the down projection matrix, and W up UK is the up projection matrix for keys and values respectively. During inference, MLA only needs to cache this CT KV, so that the KV cache has only compressed dimension into L elements, where L denotes the number of layers. In addition, during inference, since W up UK can be absorbed into WQ and WUV can be absorbed into WO, we do not need to compute keys and values out for attention, because UK and UV will be smaller than WQ, right? So this above figure has the illustrates how joint compression in MLA reduces the KV cache. So this is the figure that they are uh, giving. So this is the projection compressed KV. So to achieve this low rank compression during training to reduce the activation memory, they also perform low rank compression for the queries, even if it cannot reduce the KV cache. So using this equation. So nowadays most LLMs have rotary position embeddings or rope based rotation metrics. Rope applies a position dependent rotation matrix to the query and key vectors at each token and uses sine and cosine functions for its basis, but applies them in a unique way to achieve rotation, where the equation looks like this. However, rope is incompatible with low rank KV compression. To be specific, rope is position sensitive for both keys and queries. If we apply a rope for the keys, then the up projection weights will be coupled with position sensitive rope metrics. In this way, the up projection weights cannot be absorbed into WQ anymore during inference, since a rope matrix related to the current generating token will lie between WQ and W up projection, and the matrix multiplication does not obey a commutative law, or rather matrix multiplications are not commutative. This means that the order in which you are multiplying matters. So we must recompute the keys for all prefix tokens during inference. This will significantly hinder the inference efficiency. So as a solution, they decouple the rope strategy that uses additional multi-head queries, and they brought an equation on how to decouple this. During training, they used FP8 quantization. They used FP8 mixed precision training for better MLA stability. They used a fine grained quantization strategy, tile wise grouping of 1 cross n C elements, or blockwise grouping using NC cross NC elements. The associated dequantization overhead is largely mitigated under this increased precision accumulation. So this is the increased quantization precision process. So there NC is 128 elements. So the accumulation is upgraded to floating point 32 every 128 steps, ensuring better numerical precision while maintaining FP8 efficiency. So next is the multi-token training objective. So the idea of multi-token prediction was brought in by Meta in April 2024. This is the overall multi-token prediction architecture that they had. So in DeepSeek v3 employs D-sequential multi-token prediction modules, or MTP modules. Each module is responsible for, so there is the main model, there is the MTP model 1, MTP model 2, and so on. So similarly, there were D such modules. Each module is responsible for predicting an additional future token and not done in parallel. The kth MTP module consists of a shared embedding layer, a shared output head, so all these are shared, a transformer block, and a projection matrix M. For each prediction depth, they compute the cross entropy loss. DeepSeek v3 maintains a causal chain across prediction depths, ensuring each token is conditioned on prior MTP module outputs. So this is dependent. I mean, this one is dependent on this. During inference, they discard these MTP modules and only the main module is used, or there is an option to use the MTP modules as speculative decoding modules. So now we'll talk about the training pipeline and reinforcement learning that is used in R1 model. They apply RL to the base model without applying SFT first. This approach allows the model to explore chain of thought reasoning for solving complex problems. This is the DeepSeek R10 model. In the R1 pipeline, two stages are involved for reasoning and human alignment, and two SFT stages to act as seed for model reasoning and non-reasoning capabilities. So, model distillation is done to distill reasoning patterns from the larger models to the smaller models. For reinforcement learning, they use group relative policy optimization. At the heart of GRPO is this concept of relative evolution. This approach eliminates the need for a separate critic, making GRPO both efficient and robust. By fostering competition within groups, GRPO drives the model to consistently improve its reasoning capabilities. For the reward modeling, they used accuracy rewards and verifying if the rewards are correct. They did not use any reward neural network because they are arguing that the reward model suffers from reward hacking in reinforcement learning process, and because it needs additional training, the whole process gets complicated. For training, they only limit to structural format and do not impose restrictions on content specific bias such as reflective reasoning or promoting particular problem specific strategies. Because they did not start with SFT, they can monitor the progress of the capability of the model over time. They found that there is emergent reasoning capability of the model. It naturally acquired the capability to solve more complex tasks by extending the test time computation. So, this is increase in the average length per response with more training. Researchers found that there is an aha moment during training where the model understands that it should allocate more thinking time to a problem and re-evaluate its initial approach. This they did in R10, but in R10 there were issues such as poor readability and language mixing. So in R1 they use some human friendly cold start data. For this they collected thousands of cold start problems. They primarily focused on problems using coding, mathematics, science, logic, and reasoning. So, here they are talking about distillation and fine tuning open source models like Quen and Llama. We have also recently released a video on Llama fine tuning. Do check it out. So, for the distilled models, they only apply SFT and do not include any reinforcement learning stage, or rather, in future, they might do exploration on reinforcement learning stage on distillation. So, this is the explanation of the overall R1 model. The research that they have done is truly fascinating. If you like this video, do leave a comment. Thank you for watching.